Welcome to qnawire.
This is problem 64 of chapter 23. This problem concerns itself with the resolving ability of a telescope with respect to objects on the moon. So here we are given the diameter of the objective lens used in the telescope. This is given as 3.0 centimeters. And we're told if you have a telescope with this lens, what is the resolution and what is the minimum distance that you can distinguish so that you can distinguish two objects on the moon. So to answer this question, we're going to need a wavelength, and we're also going to need this diameter of the lens. So the equation that's relevant here is the Rayleigh criterion equation, which is theta res is going to be equal to 1.22 lambda over d. So if, say we had a wavelength, we would solve this equation and we would get this resolution here, this resolution angle. That won't tell us, though, the distance between the objects that can be resolved on the moon. So let's draw a picture of what's going on. Here we are on Earth's surface, and here's the moon. So obviously not drawn to scale, but let's say you are somewhere here on Earth's surface and you are looking at the moon here. You're looking at two objects on the moon, and the question is, with your telescope, what's the closest distance, or how close can two objects be such that they can be resolved here? So notice that here, let's suppose that here we are on the surface of the moon. These are the two objects that we want to look at. Notice that this forms a sort of angle here, theta, and this is the arc here. So if this is the angle theta, let me go ahead and label this a different color, blue, so that there's a little contrast so that you can determine that it's here. This is the theta and this is the arc. This is the separation. This equation gives us the angle theta res. This, however, does not tell us what that separation is. How close can those two objects be such that they can be resolved? So here we have theta res, and here we have this arc length, which represents that arc length. Notice that since this angle is so small, that the arc length is pretty much going to be a straight line. So let me go ahead and take that arc length and replace it with a straight line, because for small angles we can make that approximation. So let me go ahead and just replace that with a straight line, which is as good as an arc as any. Okay, so supposing theta res is small, which we expect it to be small, if theta res is small, angle is defined at that arc length. We'll call that d over the radius here of the curvature. So this radius, capital R, this is the distance between the Earth's surface and the lunar surface. So that's the other piece of information we're going to need. Okay, so not only are we not given a wavelength, we're also not given what this R is. Okay, so here, once we have theta res, all we have to do to solve for d is multiply both sides by capital R. So our answer in the end is going to be theta res times this radius. Okay, so first let's go ahead and this is going to be our final answer once we plug in theta res here, and once we determine what R is. So let's start with theta res. We know what d is, so let's go ahead and convert this to meters. This is going to be 3.0 times 10 to the negative 2 meters. What are we going to use for lambda? Well, visible light is bounded here on the lower end. This is what I found online. It's between 380 nanometers on the lower end, and on the upper end 740 nanometers. So I can't see wavelengths of this wave of 380, but this is what we're told. On average, this is the visible spectrum. This is the lower end, and this is the upper end. So what we're going to use instead for lambda, we're going to use the average of these two extremes. So lambda average comes out to approximately 560 nanometers. So 560 nanometers is 560 times 10 to the negative 9 meters. Now, if you use a different average wavelength, or if you pick any other wavelength here, you're going to get a different answer here, and that corresponds to using a different filter on your lens. So here, this comes out to like a greenish filter. So if we're just taking this, again, you're going to get different answers. If you try different wavelengths, you could try any wavelength here in the visible spectrum, and we're going to get answers that are going to be different, but they're going to be on the same order, which is what we're doing here. We're getting a rough estimate for the resolution ability of the telescope. Okay, so this is lambda average. Let's also get what this r is. Okay, so r, the distance between Earth and Moon, this is what I found. I found that r fluctuates between 356,400 kilometers when Earth and Moon are closest to the furthest they get is about 406,000 kilometers. Okay, so our average comes out to be 381,550 kilometers. Okay, so let's convert that to meters. It's going to be 381,550 times 10 to the third. And this is going to be in meters now. Okay, notice this number is way bigger than this one. So let's go ahead here and solve for theta res. So it's going to be 1.22 times our lambda, which is this average value. And let's divide that by our diameter of the telescope. This is what we get. So our angle here in radians is going to be 2.277 times 10 to the negative 5. And this is in radians. Notice this is an extremely small angle, so small angle approximations are valid. Now we could go ahead and use this in conjunction with this equation here to solve for that separation distance of two objects that can be resolved with our telescope. Now this is going to be the minimum distance. So d min is going to be equal to our average times theta res. Let's go ahead and plug this in. Our average is this quantity. Theta res is this quantity here, and here all we care about, we don't care about the units, we're just going to take the number. And we're going to go ahead and multiply this together, and we get 8,689 meters, which is equal to roughly 8.7. So that's right, approximately 8.7 kilometers. So again, depending on the wavelength that you're using, here we use 560. And depending on what you use for the separation between Earth and Moon, here we're using this quantity, you're going to get a different answer, but it should be on this order, approximately 8.799-ish kilometers. So that means from Earth's surface with a telescope of this diameter, you can resolve objects that are at least this close to one another, 8.7 kilometers. An additional point, let's suppose you didn't want to use this definition of the angle here, d, where it's arc length here over the radius. Also notice that if you formed a right triangle here, you would have tangent of theta res equal to opposite, which in this case would be d, over adjacent, which in this case would be r. Here you can solve for d as well, so d is going to be equal to r times tangent of theta res. But for small angle approximations, tangent of theta res is approximately equal to theta res. So we arrive at the same expression. And that's why we don't really care about the units here, because tangent of a radian is just a number. So here, once we make this conversion here, once we make this approximation, we just get theta res here, but as a pure number. Okay, so these two results are equivalent. So the answer here, the minimum resolution, or how close can two objects be on the moon's surface such that you can distinguish them from Earth with this telescope, with this diameter objective lens, it's going to be 8.7 kilometers. This concludes problem 64.